Welcome back friends to another video tutorial of Inorganic Chemistry Made Easy. My name is Dipanshi Avasthi and today we are going to start with the Phosphazene Part 2. So in the previous part we have discussed about polyphosphagene and the method of their preparation, but in this part we will be studying properties and the structure of phosphagene. So let's get started. Phosphagene, properties and structure. So firstly, I'll be discussing about the properties of phosphagenes. So the first property is the physical properties. So physically, the NpCl2 thrice, which is tricyclophosphonitrile chloride. So the properties are its melting point is 114 degrees centigrade and its boiling point is 256 degrees centigrade at 1 atmospheric pressure, and it is readily soluble in ether, benzene, and carbon tetrachloride. These are the physical properties of this type of cyclic phosphagenes. So another phosphagene is in the form of tetramer, so that is NpCl2 4 times, and its melting point is 123.5 degrees centigrade and its boiling point is 328.5 degrees centigrade. It is less soluble in ether, benzene, and carbon tetrachloride as compared to NpCl2 thrice. Now, on heating both NpCl2 thrice, both these cyclic forms trimer and tetramer at 150 to 300 degrees centigrade, they polymerize to an elastic product of very high molecular weight of the order of 20,000, and on further heating to 350 degrees centigrade this product get depolymerized. That means till 150 to 300 degrees centigrade, when we are heating both these products, then they are forming an elastic product which is of high molecular weight. But as soon as the temperature extends from 350 degrees centigrade or it reaches here, the product it get depolymerized. You can see this is a depolymerized product which is formed when we are heating, we are extending its heat above the 350 degrees centigrade. So it was completed, the physical properties were completed, and now the next reaction is the substitution reactions. This is another property of the polyphosphagenes. So you can see this is a phosphagene molecule which is in the form of trimer, because trimer structure it dominates. So in this you can see its structure contain 3 nitrogen atoms, 3 phosphorus atoms which are linked to each other, and the phosphorus atom are attached to further 2 halogen atoms, and here we are considering the chloride structure because we are taking chlorine as a halogen here. So in the substitution reaction, this chlorine groups, the halogen groups which are present on this phosphorus atom, these are replaceable, and in this the reagent will put its substituent will get attached here and they will replace this chlorine atom. So if we are taking KSO2F, it is a fluorinating agent, so it will remove chlorine from this phosphorus and the fluorine molecules will attach to this phosphorus atom. So similarly you can see on all the 3 locations the chlorine is replaced by this fluorine. So this is the first kind of substitution, which is the fluorination. Then if we are talking about the metal alkoxides, so this is the sodium methoxide. So in this this group OMe, which is oxomethyl group, so it is replacing this chlorine and it is attaching on adjacent positions on the phosphorus atom. So this is also substitution reaction. Then using piperidine, this group which is C5H10N, this group this replace the chlorine atoms and it is joining to phosphorus, and at all the positions the chlorines will be replaced and this group will be added. The next one is NaSCN. So this SCN group will attach to this phosphorus and NaCl will be removed. So this is another kind of substitution reaction. Now you can see this is a kind of a Grignard reagent, which is aromatic Grignard reagent having phenyl group as alkyl component. So in this, the chlorine molecules will be replaced by this phenyl group. So this is the last kind of substitution reaction. So these all substitution reactions are shown by this phosphagene molecules, and the similar reactions will be there in the case of a tetrameric cyclic product. So now next reaction is the hydrolysis. So in hydrolysis, the trimeric form, which is the phosphonitrile chloride, so when we are hydrolyzing it, then there is a removal of 6 HCl molecules. All the chlorine molecules they will be removing with the hydrogen molecule from the water, and the OH group, which is hydroxyl group, it will be attaching to this phosphorus atoms on all the 3 sides. Then there is, you can see the important thing, the main thing is the isomeric change. So generally the trimetaphosphomic acid, this trimetaphosphomic acid which is formed, in which the chlorine molecules they are replaced by the OH group, it shows an isomeric change in which it is losing this H molecule from the 3 H molecules from this, and the double bond oxygen is coming here, and this is converting from trimetaphosphomic acid to trimetaimidophosphoric acid. So this is an isomeric change which is reversible in nature. So these two products are generally formed on the hydrolysis of this trimeric form of phosphonitrile compounds. So now that was the hydrolysis in trimeric form. So now let's discuss the hydrolysis in the tetrameric form. So in the tetrameric form, when we are providing it with the water, then all the chlorine molecules they are moving with one hydrogen molecule of the water molecule, and OH groups are replacing this chlorine, and they are attaching to phosphorus atom, two groups on each position. So they are forming tetrametaphosphamic acid, which is NPOH twice 4 times, and it is also showing isomeric change and similar change as compared to previous one, and it is forming tetrametimidophosphoric acid. So in which the H group is removed from the four positions from OH group, and double bond O is present in that form. So when we are comparing the trimeric and tetrameric form, then we will see that the tetramer, it reacts with the water faster than the trimer. So you can see the reaction of tetramer is more faster when we are performing hydrolysis. The next reaction is the reaction with ammonia. So this is a triphosphonitrile chloride. So when we are reacting it with excess of ammonia, then firstly all the chlorine they will be replaced by the amine group, which is NH2. Amino group is replacing chlorine on all these positions, on 3 phosphorus atoms on the 6 positions. When we are heating it again, then it is losing NH3 group. One NH3 will be removed, and only single NH will be present at all these positions, and further heating will lead to the formation of phosphorus nitride. Means this NH3 group is removing, NH3 group is separating at each point when we are providing heat. So firstly here, then here, and at last the thing we will get is phosphorus nitride. So now the properties are over. Now we will be studying about the structure of cyclotriphosphagene, means the phosphagene structure we will be studying. So d pi p pi bonding model. When we are discussing about the structure, then we study about d pi p pi bonding model for the structure of cyclotriphosphagene. So there were several descriptions which were given for this bonding, but the model of Craig and Paddock and other one of Dever and co-workers, they are the most accepted models for this d pi p pi bonding model. So there are various assumptions which were made for this model from both the Craig and Paddock and Dever and co-workers. So firstly, you can see the cyclic triphosphagene, it consists of a planar 6-membered ring. You can see here its structure is like a 6-membered ring. So first assumption was that, and the sigma bond framework is made up of overlapping orbitals from phosphorus and nitrogen. So it is formed with the help of a sigma bonds, which are formed with the help of overlapping orbitals from nitrogen atom and the phosphorus atom. So you can see here how these sigma bonds are formed here. in the ring by the overlapping of the orbitals of phosphorus and nitrogen. The bond angles suggest sp2 hybridization of nitrogen. When we see the bond angle, then we get to know that there is sp2 hybridization of nitrogen atom and sp3 hybridization of phosphorus. So as sp2 hybridization of nitrogen is there, so two of the sp2 hybrid orbitals of nitrogen containing one electron each are used for the sigma bonding, and the third contains lone pair of electrons. So you can see here there are generally two of the sp2 hybrid orbitals. So these are the two sp hybridized orbitals which are containing one electron, and these both are involved here, one here and one here, in the sigma bonding. The one is unhybridized orbital which is containing a single electron. This is unhybridized, and this is the third hybridized orbital which is containing a lone pair of electrons. So this is sp2 hybridized orbital and containing a lone pair of electrons. Now this leaves one electron unhybridized. So this is one unhybridized in the pz orbital. Similarly, four of the sp3 hybrid orbitals of phosphorus containing one electron each are used for the sigma bonding. So phosphorus atom is forming sigma bond with two nitrogen atoms and two with the halogen atoms, or we can say the side groups, leaving one unhybridized orbital containing one electron. So in this also similarly, like nitrogen, one unhybridized orbital will be left in the phosphorus atom which will be containing one single lone pair, one single electron. So we have studied about the sigma bond, how they are formed between nitrogen and phosphorus. So now as we have discussed in the previous, unhybridized orbitals and the electron they were left in them. So now we will be studying about the pi bonds. So generally pi bonds, they are formed between the phosphorus and nitrogen by using that valence electron in the 3d orbital of phosphorus and pz orbital of nitrogen. I have discussed there that pz orbital is that one which was unhybridized and containing a single electron, and similarly 3d orbital of the phosphorus, it will be containing one electron, single electron. So this dxz orbital of phosphorus atom, it will overlap with the pz orbital of nitrogen to form d pi p pi bond, and this type of d pi p pi bonding is called heteromorphic or pseudo-aromatic pi bonding. Why it is called heteromorphic? Because there is difference in the signs, you can see charge signs, that's why it is known as heteromorphic. So what happens, the unhybridized orbital, it is containing a single electron, so it is interacting with this phosphorus. So which orbital of phosphorus? dxz. So it is in the xz plane, you can see it is in xz plane, and it is interacting with this nitrogen molecule. So there is difference in their signs, so it is known as heteromorphic or pseudo-aromatic pi bonding. This is d pi p pi bonding between dxz orbital of phosphorus with, this is the pz orbital of nitrogen. So this is the kind of interaction. So in addition to this, there are additional bonds. They can also be formed in the ring by donation of lone pair. In previous I have told you that the nitrogen, it was having the three hybridized orbital, the two were involved in making bond with the adjacent phosphorus, so one was left with lone pairs. So in addition to this type of bonding, other type of bonding which can be formed by the donation of that lone pair of electrons or nitrogen atom into the vacant. So now the phosphorus will be containing the vacant dxy and dx square minus y orbitals. So these lone pairs will be donated to either xy, dxy, or either dx square minus y square. So this will result in a formation of a coordinate bonding in the xy plane and is called pi dash bonding. This one was the pi bonding, and this one is known as the pi dash bonding, which is formed due to the donation of lone pairs of nitrogen atom to the either dxy orbital of phosphorus or dx square minus y square orbital of phosphorus. So here you can see there is a pi dash interaction in the xy plane of sp2 hybridized nitrogen and dxy of phosphorus molecules. So you can see it is in the xy plane, and in this nitrogen atom is donating its lone pair and it's coordinating. So it's a kind of a coordinate bond which is formed here. Similar thing happens here, pi dash interaction in the xy plane. So it is the xy plane, and both these are taking place in xy plane, but the difference is here the orbital is dx y, and here the orbital is dx square minus y square. So thus the bonding in the cyclo-triphosphagene involves two types of pi bonding. So one is the out of plane heteromorphic pi bonding, and the other is in plane coordinate pi dash bonding. So these are two type of pi bonding which is found in these cyclic triphosphagenes. So after this, the two scientists Dever and their co-workers, they have proposed additional interpretation accordingly. They said that dyz orbital, which is perpendicular to dxz orbital, can also overlap with pz orbital of nitrogen. In the previous that heteromorphic pi bonding we have studied, then there we studied of dxz. So Dever and co-workers, they said that dyz orbital, it can also overlap with the pz orbital of nitrogen. So thus both these orbitals should contribute equally to the pi bond. So these are heteromorphic NP, that is p pi d pi bonding, which we have studied previous, with dxz, or and this one is the homomorphic nitrogen and phosphorus p pi d pi bonding through the dyz. So in the structure it will be more clear to you. So in the first structure you can see there is heteromorphic pi interaction of pz nitrogen, the pz orbital of nitrogen, and dxz orbital of phosphorus, which we have studied previously. This is the xz orbital of phosphorus. So when their interaction is there, it is known as the heteromorphic p pi d pi bonding, because there is difference in the signals, that's why signs, that's why it is the heteromorphic bonding, heteromorphic pi interaction of pz of nitrogen and dxz of phosphorus. So the Dever and co-workers, as they have proposed that other than dxz, dyz can also overlap with this. So this is the pz orbital of nitrogen, and these are the dyz, phosphorus dyz orbital. This is in this is projecting to the front side out of paper, so you can see here. So these, when they will interact with each other, then they will form heteromorphic pi bonding. So it is a kind of a pi bonding both. This is not the pi dash. The pi dash interactions, they are formed due to the donation of the lone pair. So this is a type of heteromorphic pi interaction. This is homomorphic pi interaction. So what other thing which Dever and co-workers suggested, they said that dxz and dyz orbitals, they are hybridized to give two orbitals which are directed towards the adjacent nitrogen atoms. So here they said that to adjacent nitrogen atoms, the from this side also and from this phosphorus also, these dzx and dyz orbitals, they are hybridized. So due to that, there is the formation of the adjacent, this is the formation of an island kind of structure, which resulted into a localized 3-center bond. These are 3 centers. So this is a 3-center bond around each nitrogen atom. This is called the islands of pi character. These are called as island of pi characters, which are formed due to the hybridization of dxz and dyz orbitals. Since these islands are interrupted at each phosphorus atom, so these phosphorus atoms, these locations are known as nodes, where these islands are interrupted. And this also explains that why the cyclotriphosphagenes do not show the broad delocalization effects like that of benzene, which has simple p pi bonds. So this is the reason that this is you can see the completely, they are not covered by the electron cloud, because in benzene you can see upper side also the cloud is there, 3 carbon molecules, upper side of the ring you can see the cloud of electron is present, and in the lower side also, but here there is interruption at each phosphorus atom. So that's why this is completely do not show the delocalization effects as that of benzene. So this is a 3 center island of pi bonding in NpCl2 thrice. So this was complete information about the structure of triphosphagenes, or we can say cyclic triphosphagene, and similar thing happens in the case of the tetrameric form as well. Similar structure is there. So this was here we complete the d pi p pi bonding, in which firstly we have studied about how the sigma bonds were formed, then we have studied about how the pi bonding is there. One is heteromorphic, one was homomorphic. Then after that we have discussed about the pi dash interactions which are formed due to the donation of the lone pair of nitrogen. Then we have studied about the island model which was given by Dever and co-workers due to hybridization of d, xz and dyz orbitals, and this island was interrupted at each phosphorus, which are called node. And then we discussed that why these are different as compared to benzene, because there is also d pi p pi bonding, but it is not like benzene. It do not show delocalization effect because of this interruption. This was all about its structure and the properties. So here the phosphagene part is completed, and thank you for watching, and keep watching for the next videos. Till then, thank you.